Good morning, everyone. Today we're doing Unit 4, Lesson 4, solving 2D and 3D word problems. So we're going to look at some word problems and use everything we've learned about trig so far within these word problems. So this diagram here, or this little graphic, kind of breaks down what we've learned so far in terms of strategies to solve trigonometric problems. So whenever we have a word problem, you should consider that we should draw and label a diagram. Sometimes reading it all is hard to understand what's being asked, but if we can draw the triangle and label some of the given information and provide given information, then it's just broken down into triangles that hopefully we know how to solve. So if we take a look at what kind of triangles we've worked at solving so far, we've looked at right triangles. So if we have a right triangle, what strategy do we use? We'll use those primary trig ratios, or SOH, CAH, TOA. All right. If we don't have a right triangle, so any triangle other than a right triangle, we could have an acute triangle or an obtuse triangle. We call these oblique triangles. And oblique triangles are just any triangle that's not a right triangle. So we've looked at a couple different strategies for our oblique triangles as well. We're going to use our sine law or our cosine law. And in the last couple notes, we looked at when do we use sine law, when do you use cosine law, and sometimes we need to check for the ambiguous case as well. So we use sine law when we have that side angle pair. So if we have a side angle pair in the triangle, meaning we know corresponding side and angle length, then we can use our sine law. And we always want to use our sine law if possible because it's the easier of the two. If we're given side-side angle in a triangle, then we have to pay attention to the ambiguous case and test for the ambiguous case to see if there's going to be 0, 1, or 2 triangles possible. If we're given side-side-side or side-angle-side, then we use the cosine law. So this is either all 3 sides or 2 sides and the contained angle, so the angle made between those 2 sides. So SOH we already talked about. Pythagorean theorem is another trig formula that we should know. If we know 2 sides of a right triangle, then we're able to find the third side using Pythagorean theorem, and that formula is given there with just some rearranging to solve for different variables. Our sine law, we have 2 sets up for sine law. If we are trying to find the side, then we put the side length on top. So set up to find side length. And then this over here is the setup to find an angle. You got 2 options there when you're using sine law. And then cosine law, again, it's important to just know the pattern for cosine law. So whatever side we're working to solve, that's what we want to have the formula equal to. And then we take the cosine at the end of that formula of the angle that corresponds to that side length. So if both sine law and cosine law can be used, use sine law as it is the easier of the two, like I said. All right, so we're going to look at a couple word problems. We're going to do the setup, and then I'm going to pause the video and have you guys try to solve them on your own. But we'll go through one together. So from the top of the CN tower, which is 553 meters tall, so let's draw the CN tower. So this is 553 meters tall. The angle of depression to the Rogers Center, so we'll draw the Rogers Center over here, which is 86 meters tall. The angle of depression is 73 degrees. So we're just going to draw an angle to the top of the Rogers Center. And it says the angle of depression. So remember, the angle of depression is always made with the horizontal line. So in this case, it's an invisible kind of horizontal line, but that's going to be 73 degrees there. All right, so the question is, find the horizontal distance between these 2 buildings. Well, if I want to complete this to make it a triangle, I'm going to find the horizontal distance from the top of that Rogers Center across to the CN tower. All right, so we're going to try to find that distance there. We're going to represent it with an x. And we should always identify what our variable represents. So we're going to let x represent the horizontal distance between the buildings. All right, so we have a right triangle here because this building is straight. Some other information we can tell. Remember, when we have the angle of depression, it's going to create a Z pattern with your angle of elevation. So this angle here, our angle of elevation, is also 73 degrees. All right. We need another side length in order to be able to work with this, but we have some information about our buildings. We know that the Rogers Center is 86 meters tall. So we could say that from here to here, right, that's going to be 86 meters. And then from the top of the CN Tower to where the top of that Rogers Center would be, that would just be the difference between the 553 and the 86. So we're going to do this, and we're going to say 553 minus 86 equals 467. So we can say this side length is 467 meters. All right, so now we have a triangle where we know an angle and we know a side length. It's a right triangle, so we should want to use our primary trig ratios. I'm dealing with my opposite side and my adjacent side, so I'm going to set up for tangent. I'm going to say the tangent of theta is equal to my opposite side over my adjacent side. So we'll plug in what we know here. So my theta in this case is 73 degrees. My opposite side is 467, and my adjacent side is x. So we'll put that tangent 73 over 1 and cross multiply those. So we'll have x times the tangent of 73 is equal to 467, and then we'll divide both sides by that tangent of 73. And we should find that x is equal to 142.8 meters. So once we've solved for our unknown, we have to make sure we go back and answer the question. So therefore, the horizontal distance between the buildings is 142.8 meters. All right, let's look at some more examples. Okay, so we'll do the setup for this one, and then I'm going to get you guys to try some of it on your own. So to find the height of a cliff next to a river, the measurements shown were made. Find the width of the river, find the height of the cliff. So we have two questions here. So first we're going to work to find A. So they want us to find the width of the river. So if we look, the width of the river is that side right there, right? So for that side, I'm going to work with this triangle that's kind of laying down in the river because it looks like I have some information there. So let's find this side length x, but let's draw this triangle standing up over here so we can see what we're working with from a two-dimensional perspective. So I have my 90-degree angle, which is y. I have x up here, and I have b down here, okay? So I'm going to draw that just a little bit bigger so I can fit my numbers in there. So angle x is 48 degrees. And then from y to x, I have 18 meters. And we need to find the distance across that river, which we're going to use is for a little x. So let's let x represent the width of the river. Okay, I'm going to pause the video. You go ahead and use what you know about trig word problems and SOHCAHTOA or sine law, cosine law to figure out what x equals. If you do that, go ahead and then try to answer B as well. And when you come back, we'll have both the answers up on for this example. All right, so there's your solutions to the rest of the problem. If we set up the width of the river question using our tangent ratio, we should find that the width of the river is 20 meters. Then we can use that 20 meters and plug it in to our other problem because those triangles share a side. So that's where we plugged it in right there, because you can see that that side length is shared between the two triangles. If I highlight that on our drawing, you can see that that side length is shared on both of those triangles. All right, so when I draw that triangle and I'm trying to find the height of the cliff, so we're letting y represent the height of the cliff. Again, we're going to use our tangent ratio, and we should find that the height of the cliff is 17.4 meters. All right, we're going to look at another word problem together, and then again, I'll do this one, and I'll get you guys to try the last one. So Chris wants to find the height of the tree that is at a point D on the opposite side of a river. Chris makes measurements shown on the diagram. What is the height of the tree to the nearest meter? So again, we have two triangles. We have this triangle that goes across the river. It lays flat on the ground here, all right? And we have an oblique triangle here because we don't have any right angles in it. And then we also have this right triangle where the height of the triangle is the height of the tree. All right, and the only thing we know about this triangle, that's right triangle, is that we have a 20-degree angle, I guess, as well as that 90-degree angle. So we are to find the height of the tree, but right now we don't have enough information. But we do have enough information to find some side lengths and angles in the blue triangle, or the triangle, the oblique triangle laying on the ground. So we're going to try to find the side that they share, because if we can find the side that they share, then we have some information for that 90-degree triangle to work with. So let's draw this blue triangle that we're dealing with here. We'll draw it, oops, wrong marker. We'll draw it out here. So we have A, B, D. We know that angle A is 60 degrees. Angle B is 80 degrees. We know that side length AB is 400 meters. Right? We should be able to find this angle. If we have two of the angles, we should be able to find the other two. So let's say that angle D is equal to 180 minus 60 minus 40. So angle D, 180 minus 60 minus 80, jumping ahead. So therefore angle D equals 40 degrees. All right, now we've created this side angle pair. Right, we have a side angle pair. With our D's. So we can use that to find some information about that triangle. So let's use our sine ratio to find side length A. So we're going to say that we're going to use the setup for side length because that's what we're trying to find. So we're going to say A over the sine of 60 is going to equal 400 over the sine of 40. All right, we'll cross multiply. So 400 times the sine of 60 over the sine of 40. And we should find that equals 538.9 meters. So this side length, remember this is our shared side length, is 538.9. So if we draw now that right triangle that we have some more information that we can substitute into that. We just found some more information. So this right triangle is B, D, and C. So notice both triangles have a BD length. So we found what BD is. That is 538.9. And from our diagram, we can see the angle B is 20 degrees. And we need to find the height of that tree. So let's call the height of the tree. We'll just stay consistent here. We'll give it a little b because it's across from angle B. So let's let B represent the height of the tree. Okay, go ahead and pause this video again and work through that solution of finding what the height of the tree is. Okay, so there's your solution for the height of the tree. We should have used our tangent ratio again because we were working with our opposite and our adjacent side, and we would have found that the height was 196.1. Let's look at one more word problem. All right, so again, we're going to start with the setup, and then we'll pause the video and you guys can work through solving the question. So example 4, from the top of a 50-meter high bridge, 2 boats are seen at anchor. One boat is south 50 degrees west and has an angle of depression of 38 degrees. The other boat is south 60 degrees east and has a 35-degree angle of depression. All right, so sometimes you're going to get these bearing type problems where they're going to tell you directionally what the angle is, and these by nature create a three-dimensional problem. So we're going to have multiple triangles here again, but let's draw what we do have. So it says from the top of a 50-meter high bridge. So right from the origin of this compass, we can draw our bridge, right? Right from the top of that, directly in the middle of where these two terminal arms, if you will, where they come together, there's a bridge that's 50 meters high. We're going to put our bridge there. And then we have boats. So I'm just going to extend these a little bit. We have a boat, let's say at point A. I'm going to extend this one a bit. Oops. And then we have a boat at point B. All right, so it says one boat is south 50 degrees west. So that's what's represented here. So we have one boat that from the southern most direction goes south and then west 50 degrees. So right between our south and west on our compass. All right, so from the top of the bridge to that point has an angle of depression of 38 degrees. So remember, our angle of depression is made with our horizontal, so our 38 degrees goes there. The other boat is south 60 degrees east, so that's our other boat there between our south and our east. All right, that has an angle of depression of 35 degrees. So again, let's move that 50 meters a little bit so it doesn't get covered up. I'm gonna draw that line from there to this one, and that creates an angle of depression of 35 degrees. And then we'll just squeeze back in that 50 meters here, okay? So remember what we know about our angles of depression. Our angles of depression are going to be the same as our angles of elevation. So that 38 degrees is an alternate interior angle to angle A down there. So we can say that's 38 degrees, and angle B is going to be 35 degrees. So we have these two right triangles we're making, right? They're at an angle here, if you can imagine this three-dimensionally. We have those two triangles we're working with, and then it's wanting us to say how far apart are the boats. So the distance between the two boats, we're creating another triangle that's lying flat on the ground, all right? And we can think about the angle on the top of this triangle. I'm going to draw the triangle that's on the ground in red. So this angle that's on the ground that we're creating with the distance between the 2 points, and then also the sum of the angles that are made from the high bridge to the point, right, to the boat, the 50 plus the 60 is going to be 110 degrees for that angle there. So they want us to find how far apart are those boats, but we need some more information here. We don't have any side lengths or any other information on this red triangle. So we're going to work with our blue triangles, our 90-degree triangles up here, to try to find some more information. So again, like all of our other three-dimensional word problems, we want to try to work to find those shared side lengths, because from A to, let's call this point D, and we'll call this point up here C. Okay, so if we're trying to label these triangles, we have triangle ACD and we have triangle BCD, but we want to work to find any side lengths that they share, so that'll hopefully end up helping us with that red triangle in the end. So let's start by seeing if we can find AD, because that's one of our shared side lengths. So it's step 1, we're going to find AD. Okay, so if I was to break out that right triangle, I'm just going to draw it here next to it. Okay, we know that this is 90 degrees, this is 50, and this is 38 degrees. So if we're trying to find AD, right? This is the side we're trying to find. So that tells me we're working with our opposite and our adjacent side. So again, we're going to use our tangent ratio. So the tangent of 38 is going to equal 50 over that side, which we'll call AD, since that's what we're working to find. Okay, I'm going to pause the video. I'd like you to go through that process of finding AD. And then after you find AD, try to find BD as well. Okay, once we find those two sides, we'll come back together to continue with the problem. Okay, so hopefully you were able to find both those side lengths. When using our tangent ratio to find AD, we should see that AD is equal to 64 meters. Again, we're going to use our tangent ratio to find side length BD, and we should find that that is 71.4 meters. From there, I just set up that triangle that's sitting flat on the ground, that red triangle from our diagram, and I wrote the information we found there. So you can see that we have side length AD and side length BD we found from our previous work, and we know that the angle between them is 110 degrees. So we need to find the distance from A to B. So we're just gonna, let's call that lowercase d. So let's let d represent the distance between the boats. So in this triangle, we have side, angle, side. So we're going to use our cosine law. So our cosine law for this one, we're working to find side length d. So the setup would be d squared equals a squared plus b squared, right? It's the sum of the square of the other two sides, minus 2 times those same sides, times the cosine of the angle that's related to that side, so times the cosine of d. So we're going to plug in the information we have. So d squared is equal to 71.4 squared plus 64 squared minus 2 times 71.4 times 64 times the cos of angle D, which is 110. All right, so if we calculate all that, we should get 12,319.75049. Remember not to get rid of any of your decimals while you're doing it. You don't want to get rid of them to the end. So we'll take the square root of both sides. And we should get that D is equal to 111. So we can say, therefore, the boats are 111 meters apart. Okay, so that's it for your notes today. Try some of the practice problems so you get comfortable with those word problems.